Today our topic is Born-Haber cycle. It is very well known, interesting topic in ionic compound and ionic solid or lattice. This is nothing but a thermodynamic cycle by which, or using this cycle, we can calculate the lattice energy of any ionic lattice in terms of thermodynamical steps or process. Where in this cycle, where different thermodynamical steps like sublimation enthalpy, ionization energy, electron affinity, bond dissociation energy, atomization energy, lattice enthalpy, as well as formation energy. These all energies are involved in this cycle. And after construction of this cycle and putting all these terms in that cycle, we can find the lattice energy as well as the formation energy or any other term from this cycle applying Hess's law, which is also another thermodynamical aspect. So here we can experimentally calculate or measure the lattice energy as well as the formation energy of different ionic solids applying this cycle. Here, since our motto is to calculate lattice energy in thermodynamical way, so at first we are trying to see what is ionic lattice and what is lattice energy. Here, as we know, ionic lattice is nothing but the repetitive, gigantic, close-packed arrangement of cation and anions in a particular perfect geometry, and these geometries form from 1 mole cations and 1 mole anions in a gaseous state, but the lattice is in the solid state. The amount of energy released is called lattice energy. It is denoted by HL or U, and its unit is nothing but the unit of energy, but since it is a very high amount, so we generally express lattice energy as kilocalorie mole inverse, kilojoule mole inverse, something like that. Now lattice energy can be theoretically calculated in terms of Born-Haber equation. These two scientists proposed this type of equation by which we can calculate lattice energy where different terms are involved, like N means Avogadro number, A Mendelian constant, Z plus E and Z minus is nothing but the cationic charge and anionic charge involved in the lattice. 4 pi epsilon 0 is nothing but the SI unit coming from SI unit applied for SI unit, and R0 be the equilibrium distance between cation and anion, and N be the Born exponent. It is called Born exponent. It is used for the repulsive parameter, measure the repulsive parameter between the repulsion between two ions, similar type of charge. So theoretically, by putting this value, we can calculate the lattice energy applying this Born-Haber equation. Many other equations are there, like Born-Mayer equations, etc., by which we can calculate lattice energy. But today our motto is to calculate lattice energy in thermodynamical manner or experimental basis, which is nothing but Born-Haber cycle. Born-Haber cycle is nothing but thermodynamic cycle where different type of thermodynamic processes or thermodynamic step or thermodynamic terms are involved in this cycle. So let us see a brief history of this thermodynamical cycle or Born-Haber cycle. It is at first introduced by Max Born and Fritz Haber in 1919. They at first proposed this type of thermodynamical cycle. After that, it is formulated and something modified by Casimir Fajan, and at last, to calculate the lattice energy applying this thermodynamical cycle, we have to use Hess's law of constant heat of summation, heat summation. So thermodynamical cycle as well as Hess's law, these two combination will provide us the lattice energy of a particular ionic lattice. So this type of equations or this type of thermodynamical cycle is only applicable for ionic lattice. It must be ionic. There must involve some cations and anions, and here different thermodynamical parameters or different enthalpy changes are involved in number of steps here, and then we sum up these type of steps and produce a cycle which is called thermodynamical cycle and Born-Haber cycle. By this Born-Haber cycle and applying Hess's law, we can calculate the lattice energy in experimental manner. Now, what is Born-Haber cycle or how this cycle can be constructed, we'll see here. At first, we have to consider ionic lattice, an ionic lattice as AXN, in number of or mole of ions are involved to produce this type of AX lattice. Now, this lattice can be produced experimentally in applying two steps. One, single step of formation of the lattice, and the second one, multiple step of formation of the lattice. Now, at first, in single step of formation of the lattice, where let us consider A is a solid metal. It is found as solid state. It is heated with X2. X2 is nothing but a gas, diatomic gas, and produce AX solid lattice. So this solid, this gas, this solid. Now, if we want to balance, we can see here half mole X is involved. So this is direct process. If we directly heat solid A with gaseous X, we can produce X solid. And the amount of energy involved for this formation of AX solid, it is nothing but the formation energy of AX. It is denoted as delta HF of A. Now the second case, multiple step of formation of the lattice. Here, number of thermodynamical steps are involved or processes are involved. So at first, we have to focus on how AX is formed from A and X. So for the formation of AX solid, we need cations and anions, A cations and X anions in both in gaseous state. This is the necessary condition to produce this type of lattice. So 1 mole A positive and 1 mole X negative in gaseous state will combine each together to produce AX solid in AX solid, and here the energy involved is called lattice energy. So we have to produce A plus in gaseous state and X minus in gaseous state to produce this lattice. So our motive to produce A plus and X minus in gaseous state. So we have A solid, so we have to convert it in gas. So A solid to A gas, this is the first thermodynamical state. This process is called sublimation. Gas to direct solid to gas is called sublimation. And the energy involved here, we have to supply energy to A solid to produce A gas. It is called sublimation enthalpy or sublimation energy. Now the second one, we have to convert A gas to A cation in gaseous state. It is nothing but the ionization energy, and the energy involved, we have to supply energy from outside to produce, to eliminate one electron or to remove one electron from the valence shell of A to produce A plus. It is nothing but ionization energy 1, fast ionization energy. Now the third step, we have X2 gas. We need only X gas, one atom of gas X. So we have to break X bond. Here X2 means XX bond is there. So it may be single bond, this may be double bond, it may be triple bond. So we have to break this bond to produce X gas. So here we have to supply bond dissociation energy. It is denoted as D or delta H D. Since we need to produce AX only one atom of X, so multiplied by half. Half amount of energy is required. Since bond dissociation energy is stored in both these 2x, after breaking this bond, so we need only 1x, so half bond dissociation energy is required. Now the next step, we have produced X gas in atomic state. we have to convert it X minus, that means anion, in gaseous state. And this step is nothing but electron gaining step. It is called electron affinity, where the valence orbital of X is accept one electron from the infinity, producing X minus, and the energy released in this process is called electron affinity. Now we have produced A plus in gaseous state, X minus in gaseous state, and by combining these two ions we can produce AX lattice in solid state. And the energy involved, that means a large amount of energy or amount of energy released in this process is called lattice enthalpy, delta HL or U. So these are the single step and multiple step are involved in this thermodynamical process called Born-Haber cycle. Now, applying these thermodynamical data involved in these multiple steps, we have to construct a Born-Haber cycle of X. And since it is nothing but a cycle, so it must look like a cycle. So I am trying to draw this cycle like this. So at first, A solid, A gas. So this process is called sublimation. So here involved delta H sublimation. Now A gas to a cation gas. So this process is called ionization energy 1. So here we have produced A solid to A gas plus A cation plus. Now the second one, X2 gas to X gas, and this step is nothing but bond dissociation energy. So here involved energy is nothing but half D, since only one atom is required from this molecule. Now the second step here, X minus gas. So here also gas, here also gas, only one electron is gained from outside. So this step is nothing but electron affinity. So we have produced A plus and X minus both in gaseous state. Now when we combine these two, we can produce AX lattice in solid state, and in this step the energy involved is nothing but our lattice energy. Again, in this side, this is nothing but the single step, direct side, directly involved reaction, where A solid is react with X2 gas to produce AS solid. This is same, and in this process the energy involved is nothing but the formation energy of AX. Directly we can form A solid combine with X2 gas to produce AX solid. So we can see this is nothing but a cycle, and this cycle is called Born-Haber cycle. Now, how we can calculate lattice energy or any other parameter or any other term involved in this cycle? For that, we have to apply here Hess's law. Hess's law. So, applying Hess's law, we know that delta H formation of AX is nothing but equal to the summation of all these multiple steps. Delta H formation of this AX is nothing but the summation of all these steps are involved in this thermodynamical cycle. So it is nothing but delta H is a solid plus ionization energy of a gas plus half dissociation energy of X2 gas plus electron affinity of X gas plus U of AX solid. So delta H formation is nothing but the all terms involved in this cycle, the summation of all terms involved in this cycle. From this equation we can calculate any parameters, any terms by putting other values in this equation. So we can calculate lattice energy, since it is our motto to calculate lattice energy from the Born-Haber cycle. If we put all these thermodynamical terms, thermodynamical energy, that is formation energy of AX, sublimation energy of A gas, A solid, ionization energy of A gas, dissociation energy of half dissociation energy of X2 gas, electron affinity of X, we can rearrange the equation and find lattice energy from this thermodynamical cycle. Here I would like to say another important fact that, as we know, in this cycle here 1, 2, 3, 4, 5, 6 terms are involved, and in terms of thermodynamical view we know formation energy means energy release due to the formation, so it must be negative sign according to thermodynamics. Sublimation energy means energy required to convert solid to gas, so it must be positive. Ionization energy, it is also convert A gas to A plus gas. Ionization takes place, so we have to supply energy, so it also positive. In the case of dissociation, X2 to X, we have to supply some energy to the system to break this bond, so it is also positive. Again, electron affinity, here one electron is gained by this X gas in its valence shell from outside, so formation of X minus, so here energy is released generally, so it is negative. And lattice energy, since here formation of lattice is taking place, so since lattice is produced, so amount of energy released, so it is also negative. So here some terms are thermodynamically positive and thermodynamically negative, but when we put the value or write the Hess's law here, we never put this sign in this equation. We just apply this equation like this: delta H formation is equal to nothing but delta H sublimation plus ionization energy plus dissociation energy plus electron affinity plus lattice energy. We never put here it is negative or it is positive, it is positive, it is positive, it is negative, it is negative. We never put the sign here. This sign we never put in this equation. We just write the equation like this, and after that when we substitute these terms by the numerical values, then that numerical value must contain either positive sign or negative sign. Then we put that numerical value with their sign in this equation to get the actual lattice energy or any other thermodynamical term involved in this lattice energy calculation. Now here we have to calculate the lattice energy of KCl solid in kilojoule mole inverse unit, applying Born-Haber cycle, and some thermodynamical terms are given, or energies are given here, like delta H sublimation of potassium solid plus 89, ionization energy plus 425, bond dissociation energy of chlorine plus 244, electron affinity of chlorine minus 355, formation energy of KCl solid is nothing but minus 438. So applying this data or using this data, we have to construct at first the Born-Haber cycle of KCl, and then using this data and Hess's law, we have to calculate the lattice energy of KCl. So at first we have to construct the Born-Haber cycle of KCl. So Born-Haber cycle of KCl solid. So potassium, it is nothing but a metal solid. So potassium gas. This step is nothing but delta H sublimation. Now potassium gas to potassium ion in gas, it is nothing but ionization energy. Now chlorine, we know chlorine is present as Cl2 gas. So we have to convert Cl gas. Only one atom is required. So it is bond dissociation energy, half bond dissociation energy. Now from chlorine gas to chloride minus ion in gaseous state, it is nothing but electron affinity of chlorine gas. Now when we combine these two, K plus gas and Cl minus gas, we found KCl solid lattice. KCl lattice, so it is lattice energy U, and when in the left side, when directly K solid is into gas, we will also produce KCl solid delta H formation of KCl. So this is our Born-Haber cycle of KCl. It is constructed. Now we have to apply Hess's law. So according to Hess's law, so delta H formation of KCl is equal to delta H sublimation of K solid plus ionization energy of K gas plus half dissociation energy of Cl2 gas plus electron affinity of Cl gas plus U of KCl solid. So this is nothing but the Hess's law of KCl lattice. Now we have to put the values, numerical values from this data like this. So delta H formation of KCl is nothing but 438 kJ mole inverse is equal to delta S sublimation 89, it is positive, so kJ mole inverse plus ionization energy also positive 425 kJ mole inverse plus bond dissociation energy of chlorine also positive, so half, so 244 by 2 kJ mole inverse plus electron affinity is minus 355 plus U of solid. So we have put it all the numericals data in this equation. Now arrange this equation and we can easily find the U of KCl solid is equal to minus 438 minus 89 minus 425 minus 122 plus 355 kJ mole inverse, and equating this we can find the lattice energy of KCl. It is nothing but minus 719 kJ mole inverse. So we can see lattice energy, it is minus value. So lattice energy is released from the lattice when it is formed from its constituent ion. So here also we get minus 719 KCl for 719 kilojoule mole inverse for KCl lattice. So this is our lattice energy of KCl solid applying Born-Haber cycle. Now the second problem, we have to calculate the lattice energy of magnesium bromide solid in kJ mole inverse unit applying or using Born-Haber cycle, where other supporting data are given. So we have to construct at first Born-Haber cycle. So here I have constructed the Born-Haber cycle of magnesium bromide, where magnesium solid is taken and it is at first converted to magnesium gas applying delta H sublimation energy, then magnesium gas to magnesium 2 plus ion in gaseous state, and this transformation required two-step transformation, magnesium gas to magnesium plus 1, then magnesium plus 1 to magnesium plus 2. But here the data, the combined data, ionization energy 1 and ionization energy 2 are given combined way. So we have to represent this ionization process in combined way in the cycle. Now for bromine, as we know, bromine present in our atmosphere, in our environment as liquid. So we take bromine liquid and it converted to at first gas, Br to gas, and this process is called delta H vaporization. At first dissociate the bond of Br2 to convert Br atom. 2 Br atom is required here, so this is called bond dissociation process, denoted as D. So after that, this bromine atom to Br minus ion in gaseous state, this process, as we know, it is called electron affinity, where one electron is added in the valence shell of bromine from outside and some energy is released. Here 2 atoms of bromine get 1 and 1 electron and producing 2 Br minus ion. So 2 electron affinity is required. Now if we combine with magnesium 2 plus with 2 Br minus ion in gaseous state, we will get magnesium bromide as solid lattice. The energy involved in this process is called lattice energy. Now in the left side, here when magnesium solid is heated with bromine liquid, then magnesium bromide solid is directly produced and this process is called delta H formation. So this is our Born-Haber cycle of magnesium bromide. Now applying Hess's law, this is Hess's law, I have written here. Applying Hess's law, we can calculate the lattice energy of magnesium bromide. So delta H formation is equal to all the other terms present in the cycle, summation of other terms, delta H sublimation plus ionization energy 1 plus ionization energy 2 plus delta H vaporization plus dissociation energy plus 2 electron affinity plus lattice energy. Now we put the numerical data from the question as shown here and rearrange this data to find lattice energy of magnesium bromide, and we can see the high negative value of lattice energy, that is how much stability gained by this magnesium bromide when it is formed from its constituent ion. It is minus 2421 kJ mole inverse. It's highly stable lattice. Since higher is the negative of this lattice energy value, higher will be the stability of the lattice. Now the next problem, not only lattice energy, as I have told you, from the Born-Haber cycle for a particular lattice, we can calculate any term, any thermodynamical term from this cycle. Here in this problem, for magnesium sulfide lattice, we can calculate the electron affinity value of sulfur gas, or for this particular reaction here, sulfur gas plus 2 electron to sulfide gas. This process, particularly this process, what will be the electron affinity of this process? We can calculate from this Born-Haber cycle of magnesium sulfide. Here the other data are given here. Now, so we have to calculate the electron affinity of this process. So at first we have to construct the Born-Haber cycle of magnesium sulfide solid. So here is the Born-Haber cycle. Here magnesium solid to magnesium gas. This process is nothing but sublimation energy. Now magnesium gas to magnesium 2 plus ionization energy 1 plus ionization energy 2. Now here interesting feature, sulfur solid, sulfur present as solid. We know 8 sulfur atom are accumulate together to form S8 lattice of sulfur. From sulfur 8 to sulfur gas, this process is called atomization process. So the energy involved in this process is called delta H atomization, delta H A means atomization. Now sulfur gas to sulfide 2 minus. Here two-step process again, sulfur gas to sulfur minus gas, then sulfur minus gas to sulfur 2 minus gas. Two step, one step followed by another. So electron affinity 1 and electron affinity 2 are involved in these steps. Since our data, so we have to calculate this value from this thermodynamical cycle. Now magnesium 2 plus and sulfide 2 minus, these two ions can combine with each other in the gaseous phase to form magnesium sulfide solid. This process is nothing but lattice formation. So the energy involved in this process is called lattice energy. And in the left side, magnesium solid and sulfur solid are combined with each other to form magnesium sulfide directly, and the process is called formation energy, formation of magnesium sulfide, and the energy involved is called delta H formation. So now from Hess's law, so delta H formation is nothing but delta H sublimation plus ionization energy 1, ionization energy 2 plus delta H atomization, electron affinity 1, electron affinity 2 and U, lattice energy. So in this problem we have to calculate this E1 and EA1 and EA2, electron affinity 1 and electron affinity 2 of sulfur. So after putting all these given data in this equation and arrange it like this, we found that EA1 plus EA2 is nothing but this, and the electron affinity value for this process, sulfur gas to sulfide minus, to electron transfer process, is nothing but minus 72.4 kilocalorie mole inverse. So we can easily calculate the electron affinity of particular reaction like this from this Born-Haber cycle. Another interesting point I would like to mention, For this type of problem, you must careful about the unit. You must put the unit both the side and from the preliminary level of the equations. If you forget to put any unit in particular side, so your marks will be deducted. So in this process we have calculated electron affinity value for a particular change sulfur to sulfide using Born-Haber cycle. Here is some problems on Born-Haber cycle. Hope you will enjoy these problems using Born-Haber cycle, and thank you for watching me.